Hello everyone, this would be the fourth lecture of this series. In this lecture, we would continue with numericals on Coulomb's law. So let's begin. Example 1 says ABC is a right angled triangle such that AB is equal to 3 cm, BC is 4 cm and AC is 5 cm. Charges of magnitude 9 into 10 power minus 4 Coulomb and minus 16 into 10 power minus 4 Coulomb are placed at A and C. Observe this carefully. Find the magnitude and direction of the resultant force experienced by charge of 1 Coulomb kept at point B. So first and foremost, to draw a triangle for this, since it is a right angle triangle, we'll draw the same. So there are 3 points here called as point A. Now be careful with such triangles because the longest side here is 5 cm, that is AC. So if this point is taken as A, this should be point C, and what is remaining is point B. So this would be point B. The question says AB is 3 cm. So this distance here is 3 cm, BC is 4 cm, and this should be 5 cm. That is the values given there. Charges are placed at point A and point C. So at point A a charge is placed and that charge is given as 9 into 10 power minus 4 Coulomb. Charge placed at point C is given as minus 16, a negative charge, into 10 power minus 4 Coulomb. That's placed at point C. And then at point B a charge of 1 Coulomb is placed. So at point B the charge placed is 1 Coulomb. So question says find the, it's 1 Coulomb at point B. Question says find the force at this point B. Now there are 2 more charges kept at point A and then point C. Charges kept at point A and point C will exert a force on charge kept at point B independently, and we add the forces by using principle of superposition of vectors. So we'll first find the forces because of charge kept at point A and point C. Since charges kept at point A and point C as same polarity, that is both are positive charges, A would repel B away. So the force which A exerts on B would be a repulsive force. It will be in this direction. It's a repulsive force. It will be in this direction. That we call as F suffix A. Similarly, the force because of charge kept at point C on point B will be an attractive force, because charge at point C is a negative charge and point B is a positive charge. So it's an attractive force. It would be like this. This is called as F suffix C. So this means that it is the force which charge kept at point C exerts on charge kept at point B. We'll first find what these values are individually. We'll first find what is F suffix A. That is given by, it will be K, which is 9 into 10 power 9 into charges kept at point A and then point C. The charge kept at point A is 9 into 10 power minus 4 into charge kept at point P is 1 Coulomb by distance is 3 centimeter. Now don't forget to convert it into meters. So this would be 3 into 10 power minus 2. That is what is in terms of meter, the whole square. If we solve it further, this will give us 9 into 10 power 9 into 9 into 10 power minus 4 by this here would be 9 into 10 power minus 4 if we square this. So this term and this term gets cancelled, and what remains here would be just 9 into 10 power 9 Newton. In vector form, this force F suffix A is along AB. That's how the force is acting. We'll also find the force because of charge kept at point C, that we call as F suffix C. That is equal to 9 into 10 power 9, that is K, into Q1 is 16 into 10 power minus 4. As I told you in previous lectures, Coulomb's law is about charge magnitudes only. Into 1, the charge here is 1 coulomb, by it is 4 into 10 power minus 2, the whole square. That will be 9 into 10 power 9 into 16 into 10 power minus 4 by this would be 16 into 10 power minus 4. If you square this, again here this gets cancelled, so what remains would be just 9 into 10 power 9. In vector form, this is along BC, attractive force. Again here also the values of FA and FC are same in magnitude but different directions, so we need to add them vectorially. So we'll use the vector form where the resultant of two vectors, recall that if you have two vectors, the resultant of two vectors, if you call as R, that is given as under root of A square plus B square plus 2 into A into B into cos theta. Using same form here, if we call the net force as F, so this F is a resultant force, that's under root of, it will be F suffix A the whole square plus F suffix C the whole square plus 2 F suffix A F suffix C into cos theta. Now look at the angle between two vectors. Now here the angle between the two vectors is 90 degrees because the angle here is 90 degrees. See, this AB is a straight line. If you have a line here, this is 90 degrees because it's a right angle triangle, and since AB is a straight line, even this should be 90 degrees because for a straight line the total angle is 180 degrees. So here theta is 90 degrees and then cos 90 would be 0. And also recall that the values of FA and FC are same in magnitude. So you can write this as any one value. So that's equal to FA whole square, again FA because FC and FA are same magnitude, plus 2 into FA whole square into 0 because cos 90 is 0. So this term becomes 0, this becomes 0. So what remains is under root of 2 into FA the whole square, that is equal to FA into root 2. Now look at what is FA. FA from here is 9 into 10 power 9. So putting it back in the equation, what you get here would be root 2 into 9 into 10 power 9. That is what would be the value and 9 into root 2, solve and see it, that is equal to 12.727 into 10 power 9 Newton. Shift 1 0 this side, it becomes 1.2727 or 3 into 10 power 8 Newton. So this is the resultant force. The question says also find the direction of the force. So the resultant of these two forces, if we draw it separately, there is one force like this. There is one force like this, which we call as F suffix C, and one force which is F suffix A. Now the resultant, the sum of these two forces would be somewhere between Fc and Fa. In this case, since both Fc and Fa are equal in magnitude, the resultant would be exactly bisecting these two forces. So this would be resultant force. So the angle what makes is 45 degrees, or even here it is 45 degrees. So you can say that the resultant force makes an angle of 45 degrees with Fc or Fa. So this is the answer for this numerical. Example 2 is also similar to the previous example. Even here we take a equilateral triangle. In the previous case we had a right angle triangle, but here it is an equilateral triangle of side 3 cm. Charges of magnitude plus 5 nanocoulomb and then plus 5 nanocoulomb are placed at the corners A and B. Find the magnitude of the force experienced by a charge of 1 coulomb placed at C. Again, it's a similar approach. So we'll draw the triangle first. Since here it is an equilateral triangle, we'll draw the triangle here. So it has 3 points called as point A, point B, and then point C. In this case, all sides have same value of 3 cm. Charges are placed at points A and point B. So at point A, the charge placed is 5. This N stands for nanocoulomb. So 5 nanocoulomb. And even here at point B, it's also 5 nanocoulomb. At point C, the charge placed is 1 coulomb. So here, the charge placed is 1 coulomb. So question says find the magnitude, and it's only magnitude in this case, but we will find AB direction also. Again, as the previous examples, charges kept at point A and point B will exert a force on charge kept at point C, and we will add them by using principle of superposition of vectors or forces. We will use the principle here. We will first find the force which charge A exerts on charge C. Charges kept at point A and point C have same polarity, that is, both are positive charges. So A will push C away. So the force which A exerts on C would be along this direction. It will push it away. We call that as F suffix A. And also, charge kept at point B and C has same polarity. Even this will push it away. We'll call this as F suffix B, because both are same polarity. Now add them by using vector addition. So I use the exercise if I want to solve and see it. It is same as the previous examples. To solve it, the answer should be equal to 8.66 in 10 power 4 Newton. Just practice this to get a feel of the numericals. Example 3 says 2 point charges plus 9 into 10 power minus 8 Coulomb and minus 9 into 10 power minus 8 Coulomb are placed 0.5 meter apart in air. Find the magnitude of resultant force experienced by a charge of 1 Coulomb located at 0.5 meter from either charge. Now this is an important statement. So the question says there are two charges. If you draw charges here, so we'll call this as point A, this is point B. The charges placed here are given as 9 into 10 power minus 8 and minus 9 into 10 power minus 8. The separation is given as 0.5 meter. So this distance between them is given as 0.5 meter. Question says, find the magnitude of resultant force experienced by charge of 1 Coulomb at a point located 0.5 meter from either charge. So there's one more charge placed whose value is 1 Coulomb. This charge is placed at a distance of 0.5 from either charge. So if you place a charge, for example, somewhere here, then the distance would vary. The distance of this charge from point A is more than that of point B. Similarly, if you place a charge to left of point A somewhere here, the same case. So the charge 1 Coulomb cannot be placed along the line of A and B. The only way to place a charge such that the distance remains same between them would be to place that charge at the bisector of these two lines. So if it's placed somewhere here, in that case this distance and this distance from here and this distance would be same. So indirectly what is given here is that the charges are placed at the vertices of a triangle. Since the distances are same everywhere, the distance here and here is same, it means the charges are placed at the vertices of an equilateral triangle. There is a point which has been mentioned here. Do understand that in numericals sometimes they will not give it directly. So you need to understand the question and then decode from the question. So even this I leave as an exercise to be solved. It's very obvious from here that there are three charges at this point and this and this, and here it's an equilateral triangle. So using the previous approach, solve this. The answer would be 3.24 into 10 power 3 Newton. That's resultant force. It's given as R here, but R means resultant force. So solve and say this also. Example 4 says charges equal to Q1 are placed at two diagonally opposite corners of a square. So it's a square and charges equal to Q2 are placed at the remaining corners. So a square contains 4 points or 4 corners. At two corners which are opposite to each other, charges Q1 is placed and the remaining 2 corners charge Q2 is placed. So we'll first draw the diagram. It's a square. This is what is given here. So solution, there are 4 corners. So at 2 corners, example, call this as A, B, C and then T. At 2 opposite corners, charge Q1 is placed. Example, if the charge is Q1 here, opposite to A would be at point C. So charge here is again Q1. The remaining corners are B and D. So charge placed at point B is given as Q2 and charge placed here should be Q2. So we have 4 charges. I mean we have 4 points and two charges are same values. So question says, if the resultant, that is the net force on Q2 is 0. So take any one point of Q2, either take point B or point D. The net force is 0 on any one charge kept at point B or point D. We'll take point D as the point to solve the numerical. Question says, if the resultant force on charge kept at point D is 0, then show that Q2 is minus 2 root 2 Q1. So you need to prove it here. Again, we use same principle as the previous numericals. If we consider charge kept at point D, then charges kept at point A, point B and point C will exert a force on charge kept at point D. So we'll have three forces and we will add the force using the principle of superposition of force or vector. So we'll first find the forces one by one. We'll find the force which charge kept at point A exerts at point D. Now we don't know whether Q2 is negative or positive. So to understand this, we'll assume a case where all the four are positive. If that is the case, then we'll find the forces first. Since we assume all the four are of same polarity, that is all four is positive, then what will happen is this A would push D away. So A will push D away. This is one force. Just call as F suffix A. Similarly, this Q2, this Q1 here at point C will push D again like this. It will push it like this. This is called as F suffix C. And since even Q2 also is positive, for example, then what will happen is this Q2 will push this Q2 away. So we'll have a force because of this, because F suffix P. So you have three forces, one force like this, one and one like this. Now it is very obvious from here that these three forces can never add to be 0, because the resultant of these two will be along this only. So which means the assumption that all the four are of same polarity is not true here. So we need to modify this numerical now, and we'll assume that Q2 is negative. For example, this also say, for example, Q2, if we assume Q2 is negative, that is, it's minus Q2 and minus Q2. Now we'll see how is the problem modified. So in this case, what happens is, since Q1 and Q2 have different polarities, the charge kept at point A will pull the charge kept at point A towards itself. So the force here is an attractive force. We'll call as F suffix A. Similarly, this charge kept at point C will pull charge at point A towards itself, because charges kept at point C and point D have different polarities. So it will pull it like this. So there is one force which is towards this side. Now charges kept at point B and point D, they have same polarity, both are negative, will push it away. So one force is like this. This we call as F suffix B. We have three forces now. One force like this, one like this, one force like this, one like this and one like this. Now from here it is very obvious that these three forces can add to be 0. That is because the resultant of these two forces would be somewhere like this. So these two forces would have resultant which is like this. So this and this will get cancelled. So the only possibility that the net force kept at point D would be 0 is if either Q1 is negative or Q2 is negative. So we assume that Q2 is negative. You can as very well take Q1 to be negative and then this Q to be positive and solve the problem. The answer would be same. So we'll solve the problem now. We'll find first what is FA. So Fa is the force which is because of charge kept at point A, and this is Fc and this is Fb. We'll first find what is Fa. So Fa is equal to, we'll just write Q in this case, there's no need to put numericals here, just put K, and then we're finding force between charge capital at point A and point D, so it becomes Q1, and then here is Q2 by some distance. We'll assume that each side has a length L, which is square, so each will have same length L by L square. This is what the force is. Do remember that in case of Coulomb's law, we're just putting the magnitude. In vector form, this force is along dA because it is an attractive force. This is what is F suffix A. Similarly, we'll find what is F suffix C. So F suffix C, it is a force because of charge capital at point C on charge capital at point D. This here, this is F suffix C. That is equal to, it will be again K. The charges are, it's Q1 here and Q2 here. So we're putting it back. We get this as Q1, Q2 by distance between these should be again L by L square. It is along DC, attractive force. We'll find what is the force which charge kept at point B exerts on charge kept at point T, which is a repulsive force. That we call as F suffix D. That is equal to, it will be K. In this case, charges is the same magnitude and polarity, so it becomes Q2 into Q2 by the distance between point B and point D. Now this distance, if you solve it, would be root 2 into L. That is using simple theorem. So we look at this as say L, this as L. If we use Pythagoras Theorem, then this would be, if you call this as, for example, say point B, point, say this is point D, this is point C. Then from here, what you get is BD, the whole square would be BC, the whole square, plus CD, the whole square. That is equal to BC is L square plus L square. That is BD, the whole square. That will be 2L square. That is BD, the whole square. Or BD would be, taking a root of this, 2L square under root would be root 2 into L. That's what is given here. So it's root 2 into L, the whole square, because it is distance the whole square. Do remember that BD is root 2 into L and we're squaring it. This is along BD. It's a repulsive force. So if the net force is 0 means, it implies that the resultant of Fa, there is Fa like this, there is Fc like this. The resultant of Fa and Fc would be some force, and that force would be along this direction. So it basically means that the resultant of these two forces would balance this force. So we'll do it step by step. The first thing we do here is to find the resultant of Fa and then Fd, that I call as some F. So here F means the resultant of Fa and Ft. So again, if you solve using the vector formula, it becomes Fa, the whole square, plus F. Okay. No, we need to find the resultant of Fa and then Fc, not Ft, because Ft is along this direction. Please correct it. We need to find the resultant of these two. That is, the resultant of this and this is what we need to find out. So it will be this plus this, because Ft is the force which is going like this. Look at this F suffix B, okay, not Ft, B. So this is equal to Fa plus Fc, the whole square, plus 2 Fa Fc into cos theta. Again here, the resultant of these two would be somewhere here that I call as F. The angle between FA and FC is 90 degrees and cos 90 would be 0. So this basically becomes nothing but FA plus FC the whole square. But again observe carefully, FA and FC as same magnitude. So you can write this also as FA whole square only plus 2 into FA square into cos 90, because theta here is 90 between FA and FC, cos 90 is 0. So this becomes into 0. So finally what you get out of these two would be, it will be 2 FA under root is equal to FA into root 2. So this is the net force between FA and FC. But what is FA equal to? That's equal to K Q1 Q2 by L square into root 2. So this is the net force between FA and FC. So this force is like this. This is what is net force. But there's another force which is going like this, going out like this, as given here. It is this force here. We call it FB. So it basically means that this F is balanced by FB. So F is equal to FB, only then it will be 0. Imagine we have a box like this. If somebody pushes with a force of 5 Newton this side and pushes with the same force of 5 Newton this side, the box will be at rest. So in that sense, this FB and F are same in value. F is already given here, that F is equal to K Q1 Q2 into root 2 by L square. That is equal to, look what FB itself is. F is already given here. We put it back here. We get FB as, it will be K, this will be Q2 square. So Q2 square by, this becomes squaring, it becomes 2L square. So by 2L square. So from here, this gets cancelled, K gets cancelled, and then this Q2 here, this Q2 gets cancelled with one Q2. So what remains here would be, there's root 2, this implies there's root 2 here, there is Q1, that's equal to, there's Q2 into 2. 2 from here goes this side, becomes 2 root 2. So the answer would be, Q2 would be 2 root 2 into Q1 in magnitude. But if you recall what was Q2, it is negative. So finally what you get here is, this is what is the magnitude. With the signs it becomes here minus. Therefore using signs, K2 becomes minus of 2 root 2 into K1. This is required answer. Example 5 says, 2 point charges of 3 Coulomb and 9 Coulomb repel each other. That is because they have same polarity with a force of 27 Newton. Charges of minus 3 Coulomb are given to each of the charges, then find the force of interaction. This is a very straightforward numerical, a simple numerical also. There are two charges, say one is 3 Coulomb, other is 9 Coulomb. There are some distance between them as given here. The force between them is given as 27 Newton. There is no need to find what the force is. We just call the force as F and distance as R. So the force in this case, which would be 9 into 10 power 9 into 3 into 9 by R square. That's the required force, that is given as 27 Newton. We don't know what is R in this case. We'll find it if required. The second part says charges of minus 3 Coulomb is given to each of the charges, which means if you look at the properties of charges, we learn that charges add up. That is called as additivity of charges. So they'll add up. If you're adding charge of minus 3 here, then the new charge becomes, it is already plus 3 with minus 3, that is the charge here, and here it is 9 Coulomb minus 3 Coulomb. So charge becomes 0 and then 6 Coulomb. That's a new charge. So the force in this case we call as F1, that will be, it will be K into 0, because one charge is 0, into whatever it is, with 6 and then distance square, the whole thing is 0. So in this case, the net force becomes 0. I hope this lecture is useful to you all. If you like it, do share with your friends. Thank you.